All right, ladies and gentlemen, class recording is started. So, this next unit that we get into, you will see as you start looking at doing reading and doing homework, if you choose to do those sort of things at home, we are jumping around quite a bit in your book for this unit. We're going to start off in Chapter 2, we're going to move to Chapter 3, but then we're going to jump all the way to Chapter 17. There's a reason, tying a bunch of things together. A lot of times, classes, physical science classes, will start with this unit, but I think this is a good way to wrap up a couple of things that we've been talking about over the past couple months and talk about why we got to where we got, and use this sort of as a summary as opposed to an introduction. So, today's presentation is called Introduction to Matter, and I'm hoping that all of you can answer the first question that is up there. All right? What is matter? In order for something to be matter, go ahead, Ron. It can be, yes, that's one way, but more generally speaking, we have to have two things in order for something to be classified as matter, right? Devin, what's one? It has to have mass and take up space, or it has to have volume, right? So, for something to be classified as matter, right, it has to have mass and it has to have volume. It has to have mass and it has to take up space. Our universe, sorry, let's not go there yet. Chemistry, we discussed at the beginning of the year, and what we've been doing for the past 6 months or so, deals with matter and changes in matter. The structure, properties, and changes in matter. That's a lot of times how we define chemistry. Okay? There are two things in our universe. What are the two things that make up our universe? Let's go more general than that. Atoms, matter, and
mass. Energy.
Ah, there we go. Our universe consists of matter and energy. All right? So, if we look at what we've done up until this point, the first unit that we did in this class, after we talked about like significant digits and that kind of stuff, right, was about energy. Energy isn't matter, but what is our definition of energy?
The ability to do stuff.
The ability to do stuff, or the ability to cause changes in matter. All right? Hey, can we cut all this chit-chat, please? So we can get through this? So, the first unit that we do is about energy. Energy is not matter, but if we're going to study matter and the changes in matter, we start off with how does it happen? How do these changes happen? The next unit that we talked about was atomic theory. What are atoms, right? Why do we start with that? Because, well, what's matter made out of? Atoms, right? So let's start with atoms. And then the last two units, we've dealt with bonding, and we've dealt with chemical reactions. What happens in bonding and chemical reactions? We take atoms and do what with them? Combine them together to make new stuff, right? So all the things that we've done up until this point have dealt with either matter, defining matter, structures in matter, things like that, properties of matter, or changes in matter. And that's what chemistry class is. Now, after we finish this unit, we'll transition into more of the physics aspect, and we'll talk about how does that matter interact with each other. How do we get these things to do what we're talking about? Okay? All right. So, let's start off and let's do the basics. Okay? We know that matter comes in 3 states, right? And I think if you guys go down your outline, Roman numeral number 2, letter A, B, and C, I hope you can figure out, right? Okay? States of matter, the three biggies are what? Liquids, solids, and gases, right? And in what? Well, let's go with this first. Okay, so in this picture right here, we have water existing, or at least picturing, in all 3 states, right? There's ice cubes there, there's liquid water, and then you can't see it real well in this picture. This is a tea kettle, and there's like steam coming out of the tea kettle. So, by the way, these pictures, and I'll show you another one here in a second. These are actually taken from my kitchen. So, yeah.
I like the wallpaper.
Well, so first, that's not our stove anymore. We got a new stove. Okay. But that we do still have that awesome pineapple wallpaper in the kitchen.
You it has pineapple?
Yeah, look at it. See?
I love pineapple.
So yeah. So we haven't quite had a chance to get that changed yet. So
I love it. Don't ever see it.
like
It looks like my grandma's wallpaper though. I know.
1/508 maybe. Like, you know.
How old's your house?
It was built in 1989, so you know it's
Yeah, that wallpaper.
25 years old. You know.
My grandmother's house was built like the early 1900s, and it has like that wallpaper.
Yeah.
Except
Well, I mean,
it's blue.
you know, you could put this wallpaper in any house if you want to. We bought the people we bought our house from were an elderly couple, and so they yeah. So there was a lot of elderly couple decorating things. Like one room was just like completely pink.
Oh god.
Pink carpet, pink paint. Like it was.
Settling.
No, we got rid of that one. The priorities, like we're like, okay, pineapple wallpaper, pink carpet. Pink carpet's got to go before pineapple wallpaper goes. So.
It's like having an all.
Yeah, yeah, and like our bedroom was like this like yellow color. It was just like, yeah, we got to do something about this. So. Anyway, there are a couple other states of matter out there that we don't talk about real often, but they are important to our understanding of the universe. So first is plasma. And you'll notice, I'm not sure what happened with my outlining thing on the computer, but so you have Roman numeral number 2, states of matter, A, B, C, and then plasma is letter A again. I want to change that to D. Okay, so where it says A next to plasma, just cross that out and make that D. Okay.
And then the B.
And then the B for Bose-Einstein condensate, that should be E. So, okay. All right. So plasma. Plasma is matter, but it's not solids, liquids, or gases. Plasma exists at very high energy. What we have basically is not atoms, but pieces of atoms. Separate positive and negative charges, which you now know come from where? Where do positive and negative charges come from? Electrons and protons, right? Not neutrons. They don't have a charge, okay? So, what happens at very high temperatures, remember from previous, we haven't talked about this specifically in this class, but as things get hotter, what do they do more? They have more energy, and what does that cause them to do? They move around, right? They move faster. If you get it to a high enough temperature, the atoms can't hold themselves together. That they just separate from a nucleus and electrons into just a bunch of protons and electrons. And kind of, except it's not really a melting point. It's like a point when you can't have atoms anymore. Because it's so much energy that those things just won't stick together. Right? Well, it's just a bunch of it's just a bunch of protons and electrons. So they're just kind of mashed together. Right? Now, it doesn't exist, that state of matter doesn't exist here on Earth real often. Things like lightning, electric shocks, those are actually plasma. We're actually ripping atoms apart in the air for a short period of time, and then they reassemble back together. Okay? But if we talk about the universe as a whole, most of the matter in the universe actually exists as plasma. Because stars take protons and mash them together into other elements. But most of the mass of a star is plasma. It's just a bunch of hodgepodge of protons and electrons, and then eventually the star puts them together. And we'll talk a little bit more about that later on. But that's what we got. Okay? Good there? So plasma exists at very high energy, very high temperatures. But if we go lower and lower and lower, we actually get a different state of matter. And that state of matter is called the Bose-Einstein condensate. Okay. So you've probably heard of Einstein before, yes? Albert Einstein, yes, that's him. Okay. Bose is actually an Indian scientist who you don't hear a whole lot. What?
Create the speaker.
Say again?
Create the speaker.
I think it's named after him. I don't think he created it. So you don't hear a lot about Bose because he's Indian and we have a white person bias in this country because that's what we do.
Yeah.
You know? But he lived around the same time. He was working early 20th century, so 1900s. He's not like a Newton kind of guy or anything like that. More contemporary than that. But he made a prediction, or actually Einstein made the prediction about what would happen to matter at really, really low temperatures. And this is what he said. First, you got to be extremely low energy, like close, close, close to absolute zero. And absolute zero is approximately negative 273 degrees Celsius. And just like we talked about before, as the temperature gets lower and lower and lower, what happens to the movement of those particles? Less and less and less. Slower, slower, slower. What eventually happens is if they move so slowly, they start glomming together with each other. Glomming, that's a technical term? Glom, yeah, so, okay. They start bunching up. And entire groups of atoms behave as if they are one entity. And you might think, well, wait a minute, isn't that just a solid? Isn't that what happens in an ice cube? All of these water molecules are there. Not exactly. Think about it this way. Here you all are, and you're sitting in class, not moving a whole lot, writing, fidgeting, doing homework for another class, whatever it is, right? But you're all separate entities, right? You're all separate from one another. You can do your own thing. It might not be a whole lot of stuff, but you're all doing your own thing. What happens at really, really low temperatures is that all of the atoms basically become as one group. So it would be like all of you had to do class, but you all had to hold hands. That would be really weird. But you can't do the things that you normally do. Like, imagine when the bell rings, right? And you all had to leave, but you all had to hold hands while you were doing it.
Go to different classes.
That would be tough to do, right? Or like if one of you had to go to the bathroom, sorry, you're glommed together with everybody else, right? All those atoms behave differently at the very, very low temperatures, not like a solid, where even though solids, the movement is very small, but you're at least all still separate entities. With a Bose-Einstein condensate, that's not exactly the case. Everything basically gloms together into one big, like, super atom. Okay? Does that sort of make sense? Okay? At the extreme ends of the energy spectrum, very, very low energy for Bose-Einstein condensate, very, very high energy for plasma. Okay? Maddie, go ahead.
So is it negative 273 degrees Celsius?
Yeah, but that's what absolute zero is. Okay? So it's actually a little bit less than 273. It's like 273.15 or something like that. But these atoms don't start exhibiting that behavior until we start getting very close to that temperature. Until that point, they're still solids. They, just like you guys are now, but maybe like how you guys would be maybe during 11th period after a really, really long day, where there's even less like fidgeting and writing and previously. That's just a cold solid. It's still not a Bose-Einstein condensate. Does that make sense?
Yeah.
Somebody had their hand up over here.
Like cold just means slow moving, not actually temperature.
Well, we'll find out later in this unit that temperature is a measure of motion, which is a form of energy. Okay? So temperature actually is a measure of motion. So indirectly.
Just like when like molecules like move fast, or like makes heat.
Yeah. Well, heat is molecules moving fast, or temperature is molecules moving fast, because when they move fast, they can do more stuff. They run into things faster. They that makes sense?
Yeah.
Yeah. So it's basically kinetic energy. Temperature is kinetic energy. So. All right. So that being said, if we look at this picture of a bunch of different kinds of matter in my kitchen, yes, okay.
Is that all the counter spaces?
No. That's the edge of the little counter next to the stove. Okay. Well, again, that's not our stove anymore. So we have like a stainless steel stove now.
When was this picture taken?
I want to say probably maybe like 9, 10 years ago.
Oh.
So these pictures, yeah. So.
Did you take them on your flip phone?
No, I didn't. I did have a flip phone at that point in time. No, I took them on a digital camera. So like.
What, like a Polaroid? No, like an actual Polaroid.
So they used to have cameras that would take pictures, but it would just take pictures, and you couldn't like text on it or other thing. You know, yeah.
It's like your big camera.
Yes. So. Anyway, yeah, we still have this wallpaper. We have a different stove. This little gate right here was for my children because they were very small at the time, and that's the laundry. No, it's to keep them out of the laundry room, not to keep them locked in the laundry room. So, yeah, that's our laundry room right there. So. Yeah. So, you know. But anyway, but first, this picture is not entirely made of matter. What's in that picture that isn't matter? Plasma is matter. Well, what are your two options? Either matter or energy. So what's in that picture?
Energy.
What kind of energy specifically?
Energy.
Flash of the camera.
Lights, right? There's light in that picture, right? Because we wouldn't be able to see anything if there wasn't light. But when we look at the different states of matter, we focus in on these two, or at least I'm focusing on these two. These two have something in common, right? First, they're both solids, right? The salt and the aluminum foil, okay? But they have something else more in common. And we call these types of solids, and it doesn't have to be solids if we look at their gases too, pure substances. What makes something pure? When we say something is pure, what does that mean? 100%, right? If you go to the store and you buy a little honey bear, right? Like, you know, bear, the honey that comes in the little bear thing, right? It says 100% pure honey, right? That means what?
100% honey.
It's 100% honey.
Means that they're lying.
Doesn't have any preservatives. You know, they don't. You don't have to put anything in honey because nothing will grow in honey.
Yeah,
I know.
it's so thick that
Yeah. Yeah, it doesn't have water.
I don't think it's over 100% when they sell it.
Technically, it doesn't expire. It could crystallize. Like, honey is mostly sugar, a little bit of water. That's why it flows. But if the water like evaporates out, it can turn like solid, like all the sugar that's in there. So, but yeah, I mean, it won't grow. Like nothing will grow on it. Like it doesn't grow like mold or anything like that. So, but anyway.
Nothing was ever 100% like what it actually
Well,
says.
honey is not. We'll use that as an example. Okay, so pure substances, by definition, a pure substance is matter that has exactly the same composition. When you get a sheet of aluminum foil, what is it made out of? Foil. Good. It's made out of aluminum. Right? It's a bunch of aluminum atoms. And any sheet of aluminum foil should be made, it just has aluminum atoms. Salt, we know is made out of what? Sodium and chlorine, right? And they are joined together in what ratio? 1 to 1, NaCl. But Salt always has that same ratio no matter where we get it from. Right? Except the difference being, right? So here, let me do this, okay? Every sample of pure substance has the same properties. So all aluminum foil is going to behave like all other aluminum foil. All salt is going to behave like all other salt. Okay? But then, Jason, the difference being is there are two types of pure substances out there. And we call them elements and compounds, right? So the difference is how many types of atoms are in those things, right? They're always the same, but elements only have how many kinds of atoms? One kind of atom. But compounds will have multiple. But what's true about those multiple types of atoms?
They have the same element.
They are
Stable.
to make them a compound. What do they have to do?
Bonded.
They have to bond together, right? So, elements. Okay? Elements are substances that cannot be broken down into simpler substances that retain the original properties. There's only one type of atom that makes up elements. Question. Based on these two statements, does that mean you can't break an atom down?
No.
You can. Is it the same thing, though?
No.
No. When you break an atom down, what are you left with? Electrons and protons and neutrons, right? Those don't behave the same way as a whole atom does. So you can break an element down, you just don't have the same thing that was left, that you were left with, that you started with, right? So, all atoms of the same element are mostly the same. There's one word that you have to know that explains that statement. Right? What's the one word that explains that all atoms of the same element are mostly the same? An isotope, right? Do we at least remember that word from a long time ago? Okay? Isotopes are atoms that have the same protons but different neutrons. They are the same element, but they're not exactly the same kind of atom. But also, no two elements have the same kind of atoms, right? So, here, let's fast forward ahead to compounds, okay? Compounds, substances made from two or more simpler substances, two or more elements that are chemically bonded together in a constant proportion. Two elements chemically bonded together in a constant proportion. We sometimes refer to that as the law of definite composition. Two elements chemically bonded together in a constant proportion. And we refer to that as the law of definite composition. How do we show this constant proportion, or how do we represent this constant proportion? Yes, how do we show the ratio? With the mole ratios come from what?
Molar mass.
Coefficients. We don't want those. What shows us the ratio of atoms that are joined together?
Mole ratio.
I was thinking subscripts, everybody. Subscripts. All right.
Yeah.
When you have a formula, H2O, right? What is H2O telling you? Two hydrogens and one oxygen. Always, always, always. Right? All right. So, we can break our compounds down into simpler substances. But it's not really easy to do. Okay? Why? Why do atoms bond together to begin with? 8 valence electrons, and that's a lowest energy state. So to break them apart, what do you have to do? Not take away their energy. You have to add energy, right? Because they bonded to get to lower energy to begin with. Right? Properties of a compound are different than the stuff that makes it up. Don't worry, everybody. I can see the clock. It's all right. So, I can tell time. So, properties of a compound are different than the properties that make it up. Hydrogen and oxygen have different properties than water does. Sodium and chlorine have different properties than salt does. Okay? All right, we will pick it up from there tomorrow with mixtures, and then we'll get into properties and changes in matter. Yeah. There is some stuff on the calendar. It might be a good idea to take a look at it.